can actually produce unique concepts and hopefully unique drugs to treat this kind of a disease. So I will talk for about an hour. It's already almost 11:15, and then we will open the floor, and you can ask whatever questions you have, including any criticism. Saying, "Oh, nice work is easy. I'm here to learn." So if you have anything that will bother you, simply ask. Okay. So remember the goal: eradicating cancer in our lifetime. I'm 75 years old, so I don't have a whole lot of lifetime left for me, but you do. So let's assume that we are talking about eradicating, completely removing cancer. It's actually an unachievable goal. As you know, cancer is a very, very difficult disease. But we'll talk about, don't underestimate yourself. Human ingenuity, as I will tell you later in context with patent, their patent laws are in the US Constitution, framed by Secretary of State Thomas Jefferson, and he said, this country will provide liberal encouragement to human ingenuity. And we'll talk about that later. Okay, so what is it that we need to actually eradicate cancer? So there are certain conditions. If we are talking about the drug that will not only treat cancer, but will prevent cancer, that's a big deal. So what kind of properties should such a drug have in order to exhibit the kind of condition that needs to be met? So if I am going to come up with a drug or something that will prevent cancer as well as treat me for any cancer that I might already have, it must have several properties. Some are critical, others are would be nice if it's true. But the most important thing is that it must not be toxic for long-term use. So a drug must be non-toxic over long-term use. That's number one. Number two is, should not be easily susceptible to drug resistance. So I will mention, my next slide is about what kind of drugs we use today for cancer treatment and what kind of drugs hopefully we will have in the future for eradicating cancer. Should be affordable, of course. Should be orally taken, not by IV injection. If you know any diabetic patient, you would know that diabetic should have to take insulin injection. But there is a lot of effort going on to bring oral insulin. Instead of having an injection of insulin, if you can take a tablet, that's much better. So if there is some way we can make the next drug orally taken, not by IV injection. But there are two most important conditions that this drug must have. One is that it must inhibit the growth of cancer cells, preferably by interfering in multiple pathways and additionally killing such cells. So one thing you should know is that cancer cells are very difficult. What is cancer? Cancer is nothing but a normal cell in our body that comes out of growth regulation. So cancer is basically due to mutations in our body. Those mutations allow the cancer cell to come out of growth cycle checkpoint and keep on growing while the normal cells do not. So among all of you, you can see how this works. Remember when you were 1 year old or 6 months old, And then when you became 10, you grew rapidly in 10 years. Then when you became 20, you still grew rapidly. And then something happens. You really don't grow all that much. And then when you come to, my age, the only thing that happens is that you go down. So, did you ever think as to how or why that happens? Why is it that a little toddler, a little baby, grows rapidly to become what you are, and then you stop growing, and then actually you kind of decay? What controls this stage of life? You can also look at plants. Did you see that there are a lot of bushes? They never really grow. But there are banyan trees and a lot of those trees that are big and grow rapidly. And you wonder, what is it that keeps the little plants little and the big plants big? Or for that matter, has it ever occurred to you how a frog is the size of a frog and an elephant is the size of an elephant? What actually controls this kind of growth? So to come back to cancer, as I said, cancer is nothing but a whole bunch of mutations occurring in a single cell. The number of mutations can vary from 5, 6, 7 minimum to 70, 80 for different cancers. And there are different mutations. There are some mutations that are very important, called driver mutations. And there are some mutations that are not so important, but they contribute for passenger mutations. Okay? So there could be a single cell in my body that over the years accumulated lot of mutations and suddenly came out of that growth regulatory cycle called cell cycle checkpoint. So now they are no longer inhibited, as if they are babies, or it could be a single cell. It's a baby. So suddenly it starts growing. It has no growth regulatory control. So compared to all the other cells that are controlled by cell cycle checkpoint, this one cell came out of the cell cycle checkpoint, started to grow, and very soon will form a lump called a tumor. That's cancer. Because as it grows, it takes away nutrients from all the other cells, and the other cells are deprived, so they start to die. They don't get enough nutrients, but the cancer cell dies. And eventually, the tumor becomes so big that it actually takes away much of the nutrient, and the person, kind of becomes a victim. So if a drug is going to cure us of cancer, it must go into the tumor cell and kill it and prevent its growth. Okay? And then the last point is that that's if I have a tumor. But there are people who are more susceptible to having cancer than all of you, because remember what I said, that there are some critical mutations that can cause cancer, called driver mutations. Okay? So how do those mutations occur? So the mutations can occur over long periods of time. That's why older people are much more prone to cancer than younger people. Little kids don't get cancer unless they are exposed to carcinogens. So there are a lot of chemicals in the air. For example, I hope you don't smoke, but if you do, you should know that smoking, nicotine, tobacco products can induce lung cancer. There are, many other mutagenic agents that can, if you go and lay in the sun for a long time, you can get melanoma, things of that sort. So carcinogens induce cancer. Accumulation of mutations over age induce cancer. But you can get cancer also by one more mechanism, which is inheritance. You can actually inherit certain mutations that can make you very, very prone to cancer. and we will talk about breast cancer in the context and some of the problems associated with it, particularly with regard to patenting of breast cancer genetic detections by a company called Myriad Genetics. So those, at least those 3 or 4 conditions must be made, that your drug must inhibit growth of cancer cells if the cancer is already there. It should inhibit what's called oncogenic transformation of normal cells to cancer cells. That's when a single cell, as I mentioned, can accumulate lot of mutations, or even 2 or 3 key mutations, as I will show you, to become a cancer cell. Okay? So that's called induction of cancer. When a cell accumulates those mutations, now it becomes a tumor. And that induction of what's called, oncogenic transformation of normal cells to cancer cells, if that can be prevented, then we can prevent cancer. Okay. So how do we treat cancer today? How do the pharmaceutical companies come up with drugs for the treatment of cancer? So, as I mentioned to you, that cancer cells grow rapidly because they are out of growth regulatory checkpoints. So, cancer cells grow rapidly because those mutations lead to overproduction of certain key regulatory proteins or enzymes that will contribute to the phenotypic type of the cancer. So, what do pharmaceutical industries do? They will take a cancer, let's say lung cancer, or melanoma, or prostate, or breast, or whatever, and then they will find out what allows the cancer cells to grow rapidly. So that's called the target. So there are certain targets that you will find in every cancer cell, and those targets will promote the cancer cell growth. So if you can inhibit those targets, then you can inhibit and greatly slow down the progression of cancer. So using what's called high throughput screening, you can develop inhibitors, the pharmaceutical industry develops inhibitors that will inhibit some key targets to prevent cancer cell growth. So you presumably cannot say, but there are a whole bunch of, under drug, there are a whole bunch of either small molecules or monoclonal antibodies that will go and target, target those targets. And a list of targets is shown in the next column for imatinib or sunitinib or some of those are called receptor tyrosine kinases or monoclonal antibodies. You can see what the target, because those targets are hyper-expressed in cancer cells to let the cancer cells grow. And then there is a list of cancer that those cancers have those targets. CML is chronic myelogenous leukemia, GST is gastrointestinal stromal tumor. There are a whole bunch of them. But they all have, if you look at the next column, have side effects. The reason being that there are actually 2 problems. One is the side effect. If any of you have known anybody that underwent radiation or chemotherapy, that person will tell you how toxic chemotherapy is. Those drugs, they are very, very toxic. Why? Because remember, they strongly inhibit the target in the cancer cell. And I just mentioned to you that cancer cells are like normal cells. They are just out of regulation. So, if you strongly inhibit a target which, let's say, is hyper-expressed, hyper-produced in cancer cells, after a while, that strong inhibitor, so-called drug, will also go and inhibit normal cells. Because normal cells, although cancer cells have a lot more of these enzymes or proteins or whatever the targets are, Normal cells have them too, except in smaller amount. But if you treat a cancer patient for a long time, giving lot of that drug, they will also affect the normal cells, leading to all these problems, particularly for normal cells that grow relatively fast, like hair follicles. You know, a lot of you go to the barber every month or every 2 months because your hair grows rapidly. They become vulnerable. So a lot of chemotherapy patients lose their hair. Gastrointestinal cells, cells that line up our stomach or intestine, you know, they're always corroded by the stomach acid, so they must regenerate themselves quickly. They're relatively fast growing. They become vulnerable. So there's lots of problems, nausea, vomiting, diarrhea, and so on. Apart from, you know, weakening the patient. So what I'm trying to say is that all the chemotherapeutic drugs that you see in the list are toxic. The other problem is drug resistance. If you target a single target very strongly, the cancer cells, or for that matter, you know, any other pathogen, will see that they are being squeezed. For example, just to give you an example, let's say you want to kill me. I hope not. But let's say you decided this guy talks too much, shouldn't be here for too long, and you decided that one of you will come and kill me. There are two ways you can kill me. You can come and try to choke me, right? But I tell you that if you come and try to choke me, I'll fight you as hard as I can. Because I see that I'm going to die, and I might as well try to defend myself. See? Strong way to kill somebody. Okay. But if you kill me because you decided, you know, he might fight back, so I'll put in his drink a little bit of cyanide, just a little bit. In his food, a little bit of nicotine, a little bit of, let's say, strychnine, or a little bit of arsenic. You know, combination, I'll get very sick, and then I'll die, but I wouldn't know how to fight back because I don't really know what's killing me. So, a good drug shouldn't really be a strong inhibitor of a single pathway which the cancer cell can change. But a good drug should be something that will go inside the cancer cell and interfere in multiple pathways by which cancer cells grow, but not exerting strong inhibition to give inducement to the cancer cells to fight back. Okay. And that's where a completely new kind of anti-cancer drug comes into play, and that's from bacteria. Okay? So you'd say bacteria. What do bacteria have to do with cancer? You know, in 1892, not 1992, 120 years ago, there was a head and neck cancer surgeon in Sloan Kettering Memorial Hospital named William Collins. So he was a surgeon, cancer surgeon, so he had a lot of patients with head and neck cancer. But he observed one thing, that any time one of his patients would get infected with a bacterium, streptococcus, you know, sort of, the cancer would regress, the cancer would be gone. But the patient had an infection. So he had to kill the patient of the infection. The infection would go away because the bacteria would be there and the cancer will come back. So he said, this is interesting. He observed quite a few of his patients having that kind of a thing, and he said, why am I waiting for my patient to get infected? Why don't I get these bacteria 128 years ago? Why don't I get these bacteria, grow them, and inject them in my patients? See? Which he did. 360 patients. Success rate was 62%. 62% of his patients got well when he infected the bacteria. But he had one problem. The problem was that he had to inject live bacteria into these patients, and when you inject live bacteria into the patients, your immune system acts up, and some of these patients were advanced stage cancer patients, and they were very sick, and when their immune system got pumped up, they got very, very sick, and many of them actually died. And your drug must never kill your patient. So what happened was that, even today, there are many, many companies that are trying many microorganisms, like Clostridia, many others, to develop a bacterial anti-cancer drug system. Okay? Okay. So I will go into the details. In 1999 or so, I came to the University of Melbourne in 1979, and by 1999 I was funded by NIH to work on a bacterial infection, almost similar to William colic, which is an infection in patients called cystic fibrosis patients with this bacterium called Pseudomonas aeruginosa. And my interest and my job was to find why Pseudomonas aeruginosa causes infection in the CF patients and what to do about it. Okay? I had no interest in cancer, HIV, AIDS, malaria, or anything. I'm a bacteriologist, and I was funded to study bacterial infection in CF patients. Now, this is actually an interesting infection, because the Pseudomonas aeruginosa that would infect the lungs of CF patients would form a thin film of growth called a biofilm, and would live there for years. It would take very little nutrient from the host, so the host will not even feel that the bacteria are there. It will produce a little bit of metabolite which the host can tackle, and it's a symbiotic relationship. The cystic fibrosis patients, when they get infected Pseudomonas, will harbor them for years, and it's very difficult to eradicate the infection, because in the form of biofilm, the bacteria protect themselves from immune system, antibiotics, and so on. So what we found out was that when these bacteria are resident in the human body for a long time, for months or years, they consider the human body as their home, as their habitat, and they become protective of their habitat from outside invaders, such as cancer, such as viruses like HIV/AIDS virus, or you can sit here. You start keeping the chairs empty. Okay. So you see what I am getting at? Now you begin to realize why certain bacteria don't like cancer, because they consider the body as their home, and anything that cause or can cause harm to the human body for the bacteria resident, they find unacceptable. So they fight those external invaders by producing protein weapons, and we will talk about one such weapon called azurin. Azurin means a blue protein. Okay, so what does it do? So let's say you are growing Pseudomonas aeruginosa, and the blue protein azurin is within the cell. So if you are growing bacteria, and if you look at the growth medium, after removing the bacteria, you won't see azurin there. You add some cancer cells, out comes azurin from the bacteria, will enter into the cancer cells, but not the normal cells, and kill them by interfering in multiple mechanisms. The kind of ideal drug we talked about. So some of that is shown here. That red thing that you see in MCF7. So MCF7 is a breast cancer cell line, human breast cancer cell line. Azurin has been labeled with a red dye, and that blue thing is the nucleus, with a dye called DAPI. So you can see that in breast cancer cells, oh, that's wonderful. The red one is great. Thank you very much. Okay, so that makes life a little simpler. So you can see in breast cancer, if you treat the breast cancer cells with red dye-double azurine, azurine enters into the cell and surrounds the nucleus. So it's in the cytoplasm. Okay, you do the same human breast cells, but normal cells. See, it doesn't enter into normal cells. Then, after entering, it forms a complex with a tumor suppressor called P53 and raises its level, and then P53 will cause what's called apoptotic cell death, as well as the inhibition of cell growth through G2 cell cycle checkpoint. It would also, see this is an angiogenesis assay, meaning that these are blood vessels. You add increasing concentration of azurine and you see that it will prevent angiogenesis. Angiogenesis means blood vessel. Cancer cells have to grow very rapidly. So they need a lot of nutrients, lot of oxygen. So they have to make their own blood vessel as they grow. So if you can prevent blood vessel formation, you can prevent the entry of nutrients and they die off very quickly. So ultimately the question is, will azurine work in mice? So you can take mice called immunodeficient mice, nude mice, and you can give a subcutaneous injection of a human tumor such as melanoma or human breast cancer. And those cancer cells will grow because the mouse is immunodeficient, doesn't have an immune system. So in that model, if you now, so the tumor, human cancer cells growing in the mice, you can see the tumors, on the side, and then you inject 1 milligram azurine every day, 3 times a week, or 3 or 4 weeks, and see what happens. And if you do, you will see that the injection of azurine will allow the shrinkage of the tumor, and ultimately the tumor will be almost gone. Meaning that azurine actually works in live mice. When given in a different spot, not in the tumor, it has to go to the bloodstream, go to the tumor, because it can enter only in tumor cells but not in normal cells, and it will kill them. So that's called an in vivo assay. Okay. Now I told you that azurine is produced by Pseudomonas aeruginosa. Pseudomonas aeruginosa is a pathogen, but it's not a pathogen in the brain. But there is another bacterium called Neisseria meningitidis that causes meningitis. Meningitis is an inflammation of the brain. But then when we looked at the azurine sequence, we found out that Neisseria has also an azurine-like protein. Instead of 128 amino acids like Pseudomonas azurine, it has 127 amino acids with significant, more than 50% sequence identity with Pseudomonas azurine. But it also has an additional 39 amino acid peptide in the N-terminal. So you can ask, most of the bacteria have normal azurine, but Neisseria decided to put an additional 39 amino acid peptide in its N-terminal, in the N-terminal of azurine. Why? Then you realize that Neisseria can cross the blood-brain barrier to go to the brain. So very few molecules can go to the brain. Brain is a protected tissue. When you eat, glucose can cross the blood-brain barrier. So there is a barrier called blood-brain barrier,